Okay, so first I would like to thank the organizers for inviting me to this conference. I am, again, like Professor Marjit before me, I did my last physics class in 12th grade. So I do not know much about physics, and in fact my talk also doesn't have almost anything to do with physics, other than it involves random matrix theory in high dimensions, which a lot of contribution has come from physicists. So that is the main link. And of course it is about finance. And this is joint work with my PhD student Arnab Chakraborty, who is sitting there. So if you have hard questions, you should ask him. Okay. So spectral distribution of high dimensional covariance matrix in non-synchronous financial data. So a lot of jargon there. I'll explain them one by one. And a lot of people here have talked about covariance matrices. So that is our intent. We want to estimate the covariance matrix, but now we do not have data completely. We observe some data. So I'm a statistician, so I'm trying to estimate that covariance matrix. And I have lots of stock price processes, so the process is, in that sense, it is a high dimensional problem. So I will give a little bit of introduction and then the framework, that is the model, and then I'll talk about some common estimators of covariance, which are in low dimensions. I'll talk about the problem of non-synchronicity, again, that has been observed and tackled quite successfully in the last 10-15 years in low dimensions. And then I'll bring up the problem of high dimension and how we handle that. And we'll end with the assumptions and the theorem. And I will not show you the proof, so don't worry. So we have essentially in the last few years a lot of data because of various reasons. One is that there is more trading, so electronic trading has become increasingly popular. So there is a lot of data that is being generated. They are being recorded because our computer technology has enabled recording those. And also we can now analyze a lot of them because there is advancement in data management. So all these things together has given rise to new insights, but also new problems to handle. The framework is like this, that we have P stock prices, P stock processes, asset processes, and their prices will be denoted by where is the light? There. The prices are denoted by STJ. So J is the jth stock, and I have P of them. T is the time. I'm looking at the log price, and the simple-minded thing, the extension of Black-Scholes to multiple dimensions, I am allowing for time-varying drift and volatility. So I think this crowd, more or less, being finance crowd, knows the basic model in one dimension. We're now looking at P dimensions. So Wj is a standard winner process. Sigma is always greater than 0. It's called the spot volatility, and mu is the instantaneous drift for each j. And there is, we do allow correlation between the different prices, and that is denoted by rho, I, and j at t. Okay. Alternatively, we can write this in a vector notation. So this x is now a p-dimensional vector, p-dimensional stochastic process, and this is the stochastic differential equation for evolution of the process, and mu is now again the p-dimensional drift. Sigma is a p by p matrix, again evolving in time, and this is the instantaneous co-volatility process. And W is a p-dimensional standard Brownian motion. So I am, the W before and W now is not exactly the same, though there is a relationship between them. So now I am keeping this components of W independent and absorbing everything into the matrix. Okay, so this sigma here, the bold sigma here is the matrix which captures both the variance and the covariance, so the whole covariance matrix. And the relationship is like this. The mu is actually just tagging the mu's together. The spot volatility matrix is related to the previous sigmas and rhos in this way. Okay. So that is the notation. Whichever is okay with you, you can think of that. It is easier to do the mathematics in this framework. So this is what we will follow. The parameter of interest is what is called the integrated covariance matrix. So you can Generally this time is, I am noting by 1, this is 1 day, this is the scale of 1 day. So, for a whole day, what is the integrated covariance? Okay, so, we will have high frequency data and we want daily volatility matrix for every day. That is the parameter of interest, the sigma, capital sigma p, and this is called the integrated covariance matrix. A widely used estimator is the realized volatility matrix, and I will define it a little later. So, this estimator is based on the assumption that all the observations are observed synchronously. So, let me show you what this estimator is. So, realized covariance matrix is that if you have the lth observation of the ith stock at the time point tau Li, and it is assuming that all those points are the same for every stock, and then the realized covariance matrix is you just take the differences, and so x delta x times delta x transpose, and then you add them up. So, in the univariate setup, to estimate the variance, integrated volatility, we use just the realized variance. Now, I am looking at the matrix form of this. Okay. So, this is the realized covariance matrix, and this is a common estimator for the integrated volatility. Now, the problem arises because there is non-synchronicity. What does that mean? So, this is just some example of some data, and there is Amgen and Intel.
Sorry, just to get your notation here, could you go back to the previous slide?
Yes.
So, this capital sigma on the left hand side, is it a matrix or is it a number?
It's a matrix. It's a p by p matrix. So, delta x is p by 1, delta x. Yeah. So, we are trying to estimate this matrix. So, this is sigma, sigma transpose. So, we are using delta x transpose to estimate that for each chunk and then adding them together. So, for the integral, replace that by a sum on smaller intervals. So, that is the basic idea. Okay. So, now comes the problem of non-synchronicity, which means that the trades do not happen at the same time. So, even if we would like these taus to be the same for all I, this assumption, this is not true in real data. Okay, so, tau Li is the same as tau L for all I is required to even define this, and that is not true. And this is just a demonstration that this is where a trade is happening in Amgen. Again, lots of trades, and finally here is one trade in Intel. So, they are not happening together. So, the taus are not the same. Taus are the inter-arrival times, so that, or the event times, and they are not the same. So, there are some techniques to handle this and some standard procedures to do them. One, to convert the irregularly spaced observations to equally spaced intervals. And again, all this has been studied in the last 10-15 years in 2 dimensions. So, just finding covariance between 2 assets, and this has been very thoroughly studied. This is a very well studied field where people tried various techniques. One is previous tick interpolation, which means that you fix some times, say 20, 40, 60, and at this time if there is no trade, then take the value as the previous value. Okay, so that is the value of the stock price at this point. And in each point you do accordingly. So, at 80 the price is going to be whatever it was at this point, and so on. So, that is the previous tick interpolation. Good thing about that is that it is measurable at each time point, because you have seen the past. Another way is linear interpolation. So, this is not possible because you have not seen the future, but you essentially interpolate between the previous and the next value if you do not have a value at a point. But anyway, these have been studied and their properties have been studied. However, they are not really satisfactory, and this was observed first by Epps. It is called the Epps effect. What happens is that if you estimate the realized covariance, again this is only for 2 stocks, and I am just estimating the covariance based on previous tick and linear interpolation for various sampling intervals, and these are 2 different stocks, and one takes these are the different sampling intervals, And if you look at the realized variance using previous tick and using linear interpolation, you see that as your sampling interval goes smaller and smaller, the estimator itself also goes smaller and smaller. Okay. So, you are estimating the same quantity and you are using more and more data, and just because you are changing the sampling frequency, the estimator is just getting smaller. And one can show in various common models that this will happen even if there is non-zero covariance between the two stocks. The estimated covariance will actually converge to 0. It will not converge to the actual value, but it will converge to 0 if one has non-synchronous data. And that is what the Epps effect is. And this is another example. This is graphically, it shows that after a while it actually converges to 0. So, same thing. The estimated covariance converges to 0, whatever the actual covariance is. This is one particular example. So, these are various examples, but one can show theoretically, assuming certain models, that this is bound to happen. So, then in around 2004, Hayashi and Yoshida, they proposed this estimator, which is the Hayashi Yoshida estimator, which avoids this forced synchronization and looks at a different estimator. So, we are not looking at the realized covariance matrix anymore. We are looking at the product of delta x and delta. So in the going back in the definition here, we are looking at only the product of the same time points of the delta x. Okay. What the Hayashi Yoshida does is it takes the product of different time points, adds them together, but based on a particular condition. So, they will be, these xk and xl will be multiplied and will appear in the sum only if this indicator is 1. And what is this indicator? It is the indicator that in the kth interval, the first stock was traded. Sorry, maybe I'll show a picture. Yeah, this is better. So, these are, say, a set A and a set B, and the crosses are the trading times. Here again, the crosses are the trading times. And we are looking at, say, this difference between the x in the xk and this difference between the xl. Okay. And the product of these two things will appear only if these two intervals have a non-null intersection. So, that is what this means pictorially. So, we consider all the products and only those intervals which intersect appear in this sum. Okay. So, that is the definition of the Hayashi Yoshida estimator. And then this is in words, and I think the picture might explain this. So, this is the product. Anyway. Okay. So, and again Hayashi Yoshida estimator has been studied quite thoroughly, and they have shown that it is a consistent estimator for the integrated covariance in low dimensions. Basically, they show it only for 2 dimensions, but it is easy as long as the dimension is fixed, the same argument goes through. So, for a fixed dimension P, the estimator of integrated covariance by Hayashi Yoshida estimator is consistent. However, now we have high dimensional problems, which means that you have lots of stock prices, and you still want to estimate the covariance matrix of that. I think Anirban, is left now, he was showing a lot of stocks, and he was estimating the covariance of all of those. He was probably not using high frequency data, but if you want to use high frequency data to find the covariance matrix in such situations, then you run into the trouble, which is true in not only high frequency, any high dimensional covariance estimation problem, that you cannot estimate the covariance matrix consistently. And so, the best thing that one can hope to do, is to estimate the spectral distribution, or maybe the highest eigenvalue, things like that. Okay. So, that is what we will try to do. So, we cannot estimate the whole matrix consistently. So, what we will try to do is at least try to estimate what the distribution of eigenvalues is. So, here we want to study the asymptotic behavior, asymptotic distribution of the eigenvalues of Hayashi's matrix instead of trying to find the distribution of the full matrix. And this is a simulated example, the histogram of eigenvalues of Hayashi's estimator, and this is done with observation duration is 1 day, and we simulate high frequency data on just 60 stops. So, p is not really very high, it is just 60. The spot volatility is 1, and these are independent, which means that the original covariance matrix is 1 on the diagonals and 0 on the off diagonals. Okay, so, they are independent. So, that is the matrix I am trying to estimate. So, ideally all the eigenvalues should be 1, whereas they are not all 1 and they have a distribution, and here is where I think you must have seen distributions shaped like this in the Marchenko-Pastur distributions, that when you have high dimensional covariance matrices, then the eigenvalues are not all ones, or it should be a spike at 1, instead it has a distribution. And this is the distribution that we are trying to get. Okay, so, we are trying to capture or trying to find what this distribution is like for the specific case of Hayashi estimator. Okay. And then the number of intraday trades here is 600 and here it is 1000. So, note that this looks similar to the Marchenko-Pastur. So, it will be similar in that sense, but what exactly is it? So, that is essentially what our job is. So, for those who are not familiar with this high dimensional random matrices, this is a little bit of introduction. So, empirical spectral distribution is of a matrix A, and we will take symmetric because we are thinking of only real valued things, covariance matrices, but in general one can think of Hermitian. So, the empirical spectral distribution is defined as the distribution or the CDF, cumulative distribution function of the eigenvalues. So, number of eigenvalues which are less than equal to x. So, at every value x, so you have the distribution of that. So, lambda i's are the eigenvalues of the matrix A, and then the limiting spectral distribution is what happens to these FAPs, or does anything happen to them, do they approach any limit as p goes to infinity. So, if now the dimension goes to infinity, does this distribution go somewhere? Okay, so, this distribution is just on the real line, the distribution of eigenvalues of a real symmetric matrix. So, this is a distribution of the real line, and in general it will be just a step function. What we are trying to see is, does this have a limit when p goes to infinity, and that will be called the limiting spectral distribution. And one of the tools that is very useful in this case is the Stilljust transform. So, here is the Stilljust transform for matrix, and you can see why this will be important, because we are looking at eigenvalues, and so this is kind of the eigenequation. So, that is why this is the most natural transform to look at. And Stilljust transform plays an important role in random matrix theory in order to determine the limiting spectral distribution. And here are two theorems to give some insight on how it is useful. So, essentially we are trying to find the limiting behavior of distribution functions, and that is a difficult thing to do. So, what instead we are doing is take the distribution functions and take them to the Stilljust transform, and in that space show a convergence, and then somehow hope that the place where these distributions are converging will be related to the space where the Stilljust transforms are converging. So, this is similar to say using Levy's theorem to prove central limit theorem, that you transform to the characteristic functions and you show convergence of the characteristic functions, and then that kind of thing. So, similar thing, but now with in this setup of eigenvalues. So, the results are, one is the inversion theorem, which says that if you know the Stilljust transform, then you can get back the distribution function, and one is if the distribution functions converge, or rather if the Gn converge, that is the Stilljust transforms converge, then the distributions themselves will also converge to the same thing. So, if they converge to some place which is a Stilljust transform of another random variable, then this will also converge to G. So, these are the key theorems, and again we do not prove them, they are there. These are the key theorems which make Stilljust transform useful in this scenario. Okay. So, now I will go to the theorem. I will just state the assumptions, I state the theorem and stop, because the proof is really cumbersome. But some of the assumptions we need to make, and this particular assumption is not very satisfactory. So, if you can improve it, it will be nice. It is used, it has been used in the literature in other contexts, but what we have to do is to assume that, or at least to do our proof to go through, we have to assume that the sigma t, which is a time varying matrix, the time variation happens only in one dimension. So, you have a sigma matrix which does not vary with time, and then there is the gamma, which is in true sense a stochastic process. So, if you let all the components of the covariance matrix vary freely, then really we cannot do anything about it. So, we have one sigma which is a p by p matrix, and then there is a time component which is a scalar. So, this is the first assumption. The matrix of interest is, so the first thing we would want, so ultimately we want the distribution of this complicated thing which I defined here, this one, but the basic random block here is delta x. So, if we can find something about delta x, then we will translate it in terms of this sum and all. So, what is the distribution of delta x? The distribution of delta x with this assumption and the basic structure that we have of time varying Brownian motion becomes like this. And what that tells us is that the distribution of delta x will be same as that of sigma half dl zl, where zl's are IID normals and the dl is the diagonal with specifically the square of these as the diagonal elements, okay, because these w's are uncorrelated. So, there is nothing in the off diagonals. So, these are the diagonals. So, we break this up, we break the x into the sigma, into the diagonals, and then there is something coming from the w's. The w's are contributing the normal distribution. So, this is a simplified form of the quantity of interest, and then the Hayashi estimator, because we have delta x transpose and the Hadamard product with IKL. So, this is just writing things down, algebra. So, our goal is to study the limiting spectral distribution of this matrix S naught. But as we have discussed, we will study only the Stilljust transform, and then that will tell us about the distribution. And we need some more assumptions that P over N goes to a constant. And this is similar to the assumptions in any Marchenko-Pastur kind of theorem, that P is increasing linearly with N. And then we assume that because sigma is also growing, right? Sigma is p dimensional. It is when you fix p, it is a fixed matrix. It does not change with t, but it is growing with p. If the dimension grows, you have a bigger and bigger sigma. So, the same thing about the limiting spectral distribution of sigma comes in. So, we assume that exists, that the sigma itself has a limiting spectral distribution, and that limit has finite second order moments. Zi's are IID with mean 0, variance 1, finite moments. In fact, under the Black-Scholes they are normals even. Wi's are independent of the z's. And some more assumptions. None of them is actually very debilitating, except, as I said, the first one, which allows for time variation only in one dimension. These are quite standard in this kind of proofs. And if we, under those assumptions, we have proved this theorem, or rather Ornov has proved this theorem, that under the assumptions, almost surely the empirical spectral distribution of S naught converges in distribution to a probability transform whose spectral density is of this kind. So, going back to these things, what we have shown is that under certain conditions, the spectral distribution, the Stilljust transform of this spectral distribution converges to Stilljust transform of H, something related to H. So, this is the implication that it establishes the link between the limiting spectral distribution of the Hayashi Yoshida estimator with the limiting spectral distribution of sigma, and it does so through the Stilljust transform. So, I will just summarize. The aim is to estimate the covariance matrix of multiple assets, and in general, in this case, very high dimensional covariance matrix from high frequency data. Realized covariance is a good estimator of covariance matrix when the data is synchronous. Actually, not in high dimensions. In high dimensions, you still have only a result of this form. You do not have consistency even for realized covariance, because any covariance matrix estimation will not be consistent. So, but there also you have a spectral distribution. That result is already there. Now, the new thing is that the stock prices are non-synchronous. So, Hayashi Yoshida estimator is consistent in the non-synchronous data when the dimension is small, and now we are concerned with high dimension and non-synchronicity, and in this situation we obtain the limiting spectral distribution of the Hayashi Yoshida estimator. So, we are still in the process of getting data. As you know, in this field getting data is hard, but we have some positive links. So, hopefully in the next 1 or 2 months we will be able to have this in the actual data. And this result can be used to draw inference for unknown underlying population covariance matrix. And there is some example. I wanted to give this example because it was in one of the econophysics papers, that extreme eigenvector analysis of global financial correlation matrices. So, I think we can do similar things with non-synchronous data. And here are some references. Thank you.
Any questions?